All right, welcome back to physics. So I want to get you thinking about graphing things that are in simple harmonic motion, and we'll first take a look at a mass spring system and get comfortable with the graphs that come from that. This is a model this is a simulation run by O-Physics, and on this it shows a number of different views. So we'll try to talk through these types of different views. Notice that I've got three different types of graphs that are shown up here. So one is a circular representation of something that's moving in simple harmonic motion. I'm not going to go into that too much. I've already touched on it in class, and hopefully you'll have a chance to review that other places. But we can use some of the math for circular motion to describe things that are in simple harmonic motion. The second graph is a position graph, and this is showing energy. I could plot on here force, I could plot on here acceleration or velocity, but really this is a position graph. Right? So notice on this one I'm looking at potential and kinetic energy as the block moves back and forth, and this is going to be a curve. Almost everything on here is a curve except for force, but everything changes, all those things that change with a square of something, like the square of distance or the square of velocity or something like that, are going to be curves. And then on the far right, this is a time graph, right? And a time graph, I can look at a whole bunch of stuff. And this is what we're going to try to get our head around mostly today are these time graphs and the relationships between these. So we can plot all sorts of things on time graphs. So let's get a little bit more comfortable with it. Again, all of these are just representing this single block in simple harmonic motion. Okay, so again, these are the two types of graphs. So time graphs are the most common, but do be careful. So there are position graphs, and you can look at almost all the same things on a position graph. So this is showing position over time, right? So this is position on my y-axis and time along my x-axis. So this is going to be a time-based graph. And there are hopefully a number of things that you're able to pull out of this. So first of all, you can tell that I've pulled the block out to a maximum position. So this is my maximum amplitude, which is going to be 2. The time it takes to go through one full cycle and return to where it started from is going to be 5. I don't know, I'm guessing this is seconds. And you can pull out another couple things here, right? So the slope off of my position graph is going to tell me velocity, so I can see where the slope is a maximum, which should be at 0, 0 position. And if I had a ruler and interest, I could figure out the maximum velocity just graphically, just looking at the slope of the line. And then the last important thing to get out of this is that notice that my peaks are at the same height. Right? So the position it goes to, it returns to the same position. So all of that potential energy gets converted into kinetic energy, and none of it gets lost in those transitions, so there's no dampening, there's no friction that's happening in this. Okay, so let's look at it. So there are a few more things that you should be able to get out of the graph. So this is the same graph, but let's think about the position function that's given to you. So this is an equation that's given to you, and it looks like this shown below the graph there. Remember, A is going to be my maximum amplitude, right? So I could look at this graph and say, well, in this system, A should be 2. I'm going to look for omega t plus phi. So phi is my offset here. So this is a cosine function. So cosine of 0 is going to be 1. So that means at my 0 time point, that for this cosine function to be correct, that my 0 time point should be a maximum, and a positive maximum. Right, and that's what I see. So I can look at this and tell that, well, this is just a normal cosine. There's no offset. It's not shifted to the left or to the right. Now, if my graph was starting someplace where my 0 time point was over, like where the 2 is, then I've got something to figure out. So there's some offset. So, so notice if I shift by my offset is really much how much it shifts to the left, right? So if I started at position 0, that would be an offset of pi over 2. If I started at negative maximum, that would be an offset of pi. And if I started at over here, well, that would be an offset of 2 pi, but that's redundant. The last thing is the omega. So omega is my angular frequency. This is the same thing same value that we used in rotational motion. So omega represents the angular velocity in rotational motion. Here we call it angular frequency because it's only specific to velocity at the endpoints. But the formula for this that you're given is that omega, angular frequency, is 2 pi times the frequency, or 2 pi divided by the period. Well, I mean, I can look at the period here, right? So my period is going to be 1 to the power 5, right? I'm assuming seconds. So this is going to be 2 pi over 5. Right? So we can figure out, given these choices, right, that if my amplitude's 2, and omega is going to be 2 pi over 5, and my offset is 0, that I'm liking, which is B on this one, is the best choice. Right? So again, we have a lot of information to get out of a position graph, including the formula for the exact location of the position. Okay, so in addition to a position on a time graph, you can also look at velocity on a time graph. And again, velocity is the rate of change of position, so I can take the derivative of my original position function. And when I take the derivative of a cosine function, it becomes a negative sine function. Notice that now omega shows up in the front when I take the derivative here. Right? So notice that the amplitude here, so when my sine function is 1, it can be 0 or 1, right? So it's the minimum and maximum for sine functions. And so if I'm going by maximum, when my sine is a 1, right, that means that this maximum that I read here is going to be A times omega. Right? So this is not the amplitude, this is the amplitude times the angular frequency. Right? So you can get a number of things from this, right? So you can see the maximum velocity. So my maximum velocity is getting up to minus 2.5 and positive 2.5. You can also get from this the period, right? So from one maximum velocity here, like 3.5, to another maximum velocity at 8.5, right? So that's 5. So it's the same system that we were looking at earlier. And also I can look at the offset. So phi shows up again. So what is my offset? Well, what do I have here? I have a negative sine function, right? So on this graph, this is a sine function, meaning that I'm starting at 0, and there's no offset from this, because my sine function goes from 0. My positive sine function would go up from 0. My negative sine function goes down from 0. So by looking at this graph, I can tell that my offset for this graph is going to be 0. And so anyway, a number of things you can get from a velocity graph. And lastly, acceleration is going to be the rate of change of velocity. In this case, I'll take the derivative of my velocity equation, and I'll end up now with a negative cosine function. So notice the maximum amplitude here, my acceleration, which is just over 3, we'll call it 3.2. That's going to represent amplitude, maximum amplitude, times the square of angular frequency. So again, my cosine function, at some points this can be 1. It can't have a value greater than 1. So when that's 1, my maximum acceleration is going to be A times omega squared. So these are the three main functions that we'll look at, but we can also look at force, which is related to acceleration, right? So mass times acceleration. So it's going to be a similar shape, and energy as well. So just as a reminder, right, these are all representing the same object in motion, and they're starting at the same point. So my position graph is going to start out with a positive cosine function, and my velocity is going to start out as a negative sine function, and my acceleration is going to start out as a negative cosine function. And then all of these can be related to each other, right? So as you're going through the equilibrium position here, you should be a maximum velocity and 0 acceleration. So the last thing to consider on these graphs is going to be energy. Energy is a function of time, shows up a lot. So really important distinction though. So I'm going to have sine and cosine functions, but it's not going to be oscillating about the 0 point, because I can't have negative energy. Right? So in this one, right, the center of my graph, the center of my sine function, or cosine function, is going to be up around, what, 4.5 or something. So really important, I'm not going to have negative energy. I can't have negative kinetic energy, and I'm not going to have negative potential energy. Notice that when one's a maximum, the other one's zero, right? So when I have maximum kinetic energy, I have zero potential energy, right? So my block is fully in motion and none of the energy is stored in the spring. Importantly, notice again that the peak remains the same. So the same height is maintained, so I'm not losing energy, right? I would have the same period, right? It would still go back and forth in the same amount of time, but I could lose energy and that could go less far. And notice that these technically are cosine functions, right? So my potential energy is going to be a positive cosine function, and my kinetic energy is going to be a negative cosine function. All right, so notice these are opposites of each other, or they're out of phase by pi, if you like. Okay, well, let's look at a whole bunch together. So this looks sort of complex, but if you look at it one bit at a time, it'll make more sense. So here I'm looking at displacement in x, velocity in green, displacement in black, velocity in green, acceleration in blue. And you'll notice that displacement and acceleration are exact opposites of each other, right? So these are both cosine functions, although acceleration is starting out as a negative cosine function and displacement starting out as a positive cosine function, right? So they both become zero at the same time, they both become maximums at the same time. And hopefully this makes sense to you when you think about a mass spring system. What's happening is oscillating back and forth, and when it's at maximum displacement, it's going to have the maximum acceleration, or the maximum force pulling it back towards the equilibrium position. Again, when you stretch that spring, that's going to be where you get the largest force and when you have the largest stretch. Notice the velocity is the odd one here. So the velocity is going to be the sine function is composed to cosine functions. Again, and velocity is going to be zero when displacement is a maximum. And we can correlate these. So we can look at different time points, right? So if I look at one full period, which is going to be from where my displacement starts at a maximum and then returns to a maximum, right? That's one full period. I call that t. Right? When I'm halfway through my period, right, my block is all the way on the other side. So there's notice at those time points. So when I first start, and then when I'm halfway through, and then when I've returned, you notice that my velocity is zero. The block's all the way on one side or the other. My position is a positive or negative maximum, and my acceleration is the corresponding positive or negative maximum. So we can line all these up, and it should make sense for what you expect when a block is at an individual position. And again, from this I can get the period. So here we go, simple questions. Let's see, what's the acceleration of the system when x is equal to 0? So when my position is 0, right, so I'm going to read this as position is 0, so I'm going to look at it as a black line. This is not time equals 0, this is position equals 0. And I'm going to look at the blue line, which is acceleration, and my acceleration is also going to be 0 at that time point. Notice it happens at every time that my position is 0. That's where my spring is relaxed, and I should have no force and therefore no acceleration acting for that brief instant as it passes through the equilibrium position. What's the acceleration of the system? Is that is maximum positive displacement. So now I'm going to go to one of these maximums here. So I'm going to, when it says maximum positive displacement, well, let's go over here. So here at 3 1/4 seconds, I have maximum displacement. Let's see, acceleration is all the way down at -8. So maximum positive displacement for my mass is going to be maximum negative acceleration. So D is the best answer. What is the acceleration of the system when x is at a maximum negative displacement? So now I'm going to look at my negative displacement here, and now I have a maximum positive acceleration. And so I'm reading this black line, which is position, and that's going to tell me a maximum acceleration. All right, so what's the velocity when I'm passing through equilibrium? Well, when I pass through equilibrium, that's the point I'm going to be going the fastest, right? So when I pass through equilibrium, I'm going to be either at -4 on this graph, but it's a maximum velocity. And the next time I pass through equilibrium, I'm at positive velocity, but a maximum. So velocity is going to be either positive or negative, but it's going to be a maximum magnitude. So A is the best answer for this choice. A few more examples. So what is the velocity of the system when x is at a maximum displacement? So velocity when we're at maximum displacement here, maximum displacement means that I'm all the way at the one end or another of oscillation, and so I'm going to have a zero velocity. So I'm hoping that you're getting the oops, let me reset. So I'm hoping that you're getting a feel for what's happening and being able to look at these graphs. And really what we're looking at is how these graphs change over time. Right? And we've looked at these far graphs on the right here, right? So as position decreases, my velocity is increasing, acceleration is increasing, and so on. So I need you to be able to interpret the graphs. From the graphs you can get period, you can get velocity, you can get amplitude, all sorts of things. And I also need you to recognize that this is a time graph. Position graphs are a little bit different. That position is just going to be going back and forth. So in this case, showing the mechanical energy and the potential and kinetic energy that are just going to oscillate between the two. I can only think of one thing that's ever a straight line, and that would be on a position graph, force. So force is going to be variable, and force is going to be a straight line on a position graph, but everything else that I can think of is going to be a sine or cosine function or a curve if it's on a position graph. Anyway, I hope that's helpful. I'll talk to you soon. Bye.